Imagine trying to run like a massive AI supercomputer on a smartphone battery.
Yeah, or keeping a server from melting down when thousands of users hit it all at once.
Right. So today, you and I are going on a deliberate, measured deep dive into the NCP-GENL exam. We are mastering AI inference optimization by tackling 7 specific practice questions sequentially, and we are not going to rush this.
No, we really can't rush it, because if you're building real-world AI applications, knowing this stuff is the difference between a system that scales effortlessly and one that just, crashes.
Completely crashes. Okay, right into it. Question 1. When deploying a large language model on edge devices with strict power constraints, which quantization strategy most effectively reduces memory bandwidth utilization while preserving acceptable generative coherence? The correct answer is A.
So here we're talking about post-training quantization. Basically, a model's weights, its learned knowledge, are usually stored in a format like FP16.
Right, the highly detailed 16-bit floating point decimal stuff.
Exactly. Quantization chops that down to a much simpler 8-bit integer, or INT8.
So it's like compressing a massive high-res WAV photo into a JPEG, right? You save a ton of space, but the picture is still totally recognizable.
That is a perfect way to visualize it. You lower the memory bandwidth without losing the core logic.
Love that. Let's move to the next. Question 2. In a high-throughput deployment scenario, how does paging the key value cache improve the overall efficiency of the inference server? The correct answer is D.
Now, this is a brilliant computer science trick.
Yeah.
Without paging, a server tries to store a user's prompt in one massive continuous block of memory.
But prompts are all different lengths.
Exactly. So you end up with these, unusable gaps everywhere. Paging the key value, or KV cache, breaks that memory into small, non-contiguous blocks.
Got it. It basically stops your memory from turning into Swiss cheese. You avoid fragmentation.
Yeah, exactly. So the GPU actually utilizes its memory efficiently instead of wasting it on empty space.
Makes sense. Okay, let's scale up. Question 3. When training a foundation model that exceeds the memory capacity of a single graphics processing unit, which distributed strategy specifically partitions the model's distinct layers across multiple devices, the correct answer is B.
So the answer is pipeline parallelism. When the model is just too big, you literally divide its structural layers across multiple GPUs.
Oh, wow. So it acts like a factory assembly line. GPU 1 builds the chassis, then passes it to GPU 2 to install the engine.
Precisely. It keeps the whole system moving to handle those massive foundation models.
Nice. All right, on to the next. Question 4. During a performance analysis of a generative model, you observe high utilization of memory bandwidth, but very low compute core activation. What is the most appropriate conceptual approach to resolve this bottleneck? The correct answer is C. But wait, if the compute core is barely working, why are we stuck?
Because you're facing a memory-bound bottleneck. The GPU's brain is basically starving for data, just waiting around while the system struggles to fetch information from memory.
Oh, I see. So what's the fix?
The fix is kernel fusion, which combines multiple execution steps into fewer operations.
Oh, so you minimize the redundant back and forth trips to memory. You keep the data on the chip longer so the GPU actually does math instead of just waiting.
You got it.
Yeah.
It keeps the GPU computing.
Okay, the hardware is humming. Question 5. To improve the reliability of a model solving complex mathematical word problems, which prompting methodology generates multiple diverse reasoning paths and selects the most frequent final conclusion? The correct answer is A.
Self-consistency prompting. Instead of betting everything on a single chain of logic.
Which could definitely contain a hallucinated math error.
Oh, absolutely. So instead, you force the model to solve the problem several different ways independently.
And then you just look for the consensus. It's like asking 5 different experts and going with the majority rule to avoid single path errors.
Exactly. And if you want to optimize getting the right information to the model in the first place, well, you need routing.
Which brings us to question 6. In a retrieval augmented generation system, what is the primary purpose of implementing a semantic routing layer before the prompt reaches the large language model? The correct answer is D.
Semantic routing analyzes the user's intent first. Before a query ever hits an expensive, heavy model, this layer directs it to a specialized database.
Or like a faster, smaller model based on what the user actually needs.
Yep. It optimizes context and latency.
Like a triage nurse at a hospital emergency room figuring out exactly which specialist you need before you even enter the ward. That saves time. Okay, finally, question 7. When utilizing low-rank adaptation for fine-tuning, what is the primary structural benefit compared to traditional full-parameter fine-tuning? The correct answer is C.
Low-rank adaptation, or LoRi, avoids the crushing cost of retraining an entire model. It injects tiny, trainable decomposition matrices into specific layers.
While freezing the original weights. Right, but hold on. If you freeze the original weights, how does the model actually learn anything new?
The new knowledge lives entirely inside those tiny injected matrices.
Wait, really?
Yeah. It drastically reduces the number of trainable parameters you have to deal with, and it saves massive amounts of memory.
That's incredible. So today we deliberately mapped out how quantization shrinks models, how paging prevents memory Swiss cheese, and the assembly line of pipeline parallelism. We tack in memory bottlenecks with kernel fusion, forced consensus with self-consistency prompting, triage queries with semantic routing, and injected new knowledge via LoRa. It really makes you wonder, if we can optimize these behemoths down to run on our edge devices, what happens when?